Amazing. I think we are live. Um, uh, where do I set that? Sorry, YouTube wants me to set up my, it wants me to adjust my bit rate. Um, Anyways, we'll go with whatever we have right now. Um, Cancel. Let's do that. Let's tell people we're online. Um, yeah. So, hi everyone. Um, um, what is it that we want to do today? Uh, so we've been working on SPI an device driver for I2C to SPI bridge, and specifically the NXP SC18IS606. So basically, this guy. Yeah. Um, and mostly everything seems to be right. Well, not everything seems to be right. It's all working right. I'm just connecting a wire because demos usually fail because of wires, not code. If you have that experience. Okay, cool. So the aim of today's stream is to basically, we have the driver working, and I'll show you a demo right now. We have the driver working. Let me just hook up my UART to TTL, and I probably need to hook up my MCU. Okay, wait. SBA, I think SBA is either PB6 or something. PB9. PB9. Let me see. Yeah, so another. So it gets connected. So PB9, and that's this is SPI display basically. Let's see if we can operate our SPI display via I2C. So I believe that this should now be running. Something's wrong. Oh, yeah, of course. Of course. So just one moment. As we all talk, I shall set it up again. So I believe the red one is CS and the orange one is MOSI. So the red one is CS SS0. And ground is fine. Red one is CS. Okay. And then I believe the orange one is MOSI. We do need a clock signal somewhere there. Well, that's fine for now. Master out lay in. And then we do need a clock signal. Which one is the clock one? Yeah, you're a clock. Clock is grounded. Okay, let's see. Uh-huh. So what do you see? What you see here is a device running the Zephyr display sample, and I'll show you just now. I think some wire got unplugged again. Something got unplugged. Yeah, this is why you need to set up stuff on a breadboard really hard. PB7, PB9. Just, uh, let me remove it and try some other way. And I reset everything. So there you go. That's the Zephyr display demo, and this is an SPI device that we are controlling from I2C via our bridge. So the actual code that I'm running is here. Blah, blah, blah. The actual code that I'm running is PF, and then we're gonna do display. So samples, drivers, display, display. Yeah, this is the actual code that I'm running. So this is just um, this is a sample that runs basically uses sample to control displays. It's a display sample that's in Zephyr. So as you can see, the link down here, Zephyr samples driver display, and the overlay that we're using is this one. So our overlay, as you can see, connects an I2C controller, and then under that I2C controller, we plug in our SC18IS606 bridge, and then in that bridge, we have a Mach 7219 display. So in the end, this guy, in the end, okay. So I2C to the SC18, and then into the display. And obviously, some wire got disconnected. Whichever one, I don't know which one. Oh, I think I know which one. Red, we say display select. Should be working. Should be okay. Yeah, cool. That works. So forget the hardware for now. I'm gonna disconnect that anyways. It's a bit distracting. Let's actually write some code. So what we basically have there is Zephyr running SPI demo via I2C, and our code is mostly working. Well, all working, although there are some how do I say this? There are some uh, I need to consider the correct word. There are some bugs that are going to reveal themselves later that I think we ought to deal with now, and then we need to clean up the code a little bit and squash the commits so that we can actually make the code ready to be merged into Zephyr, and we can have this Zephyr code out there in the wild, ready for use by anyone. So first of all, let's just explore what we've done so far. And then after we've explored what we've done so far, I think I'll be able to pinpoint what changes we need to make. And then after that, we can make those changes and actually ship them out. So get if main to now. So just walk through this diff and see what's happening. So this is fine. We had configure our CMake lists for the driver itself so that we can point the driver to the source file. And then we had to add a kconfig option so that you can use kconfig to select this driver. And then inside kconfig, we had to set it up so that number one, the driver you can set up the driver, and then the driver uses I2C, so it chooses it for itself. You don't have to choose it for that. And then we also set up initialization priority that coincidentally I think needs to be lower than needs to be greater than the I2C one, which means it needs to be it needs to come later, so that you enable I2C to be initialized before the computer tries to initialize this driver. Okay, cool. And then after that, we added our own our driver, which is a few lines, but it's quite clear. So in here, most of the stuff is really standard. We just added the Zephyr headers that we needed. We made a data. We made a data struct to hold on our mutable data. We made a configuration struct to hold on to configuration items, and these are some of the things that we need to modify. And then in the other stream, in a few streams before, I worked on mutexes because this driver has an SPI bridge and has a GPIO bridge. And what you don't want to do is you don't want the GPIO bridge to grab the SPI bridge while you're using it, or you don't want the SPI bridge to grab the GPIO bridge while you're using the GPIO bridge. And in order for us to prevent that, we implemented mutex, and this is why you see there's a mutex here in the data, the first thing in the data. And then we collect our mutex, we can claim the device, and then after using the device, we can release the device. And basically, most of today's modification is going to be around this mutex so that we can transfer all the data transfer to behind the mutex, because that's usually when you grab the bridge. So we want all the data transfer to happen behind the mutex, and then excuse me. So that way I squared C can, I mean, SPI can send data without disrupting GPIO, and GPIO can send data without disrupting um, SPI. And then the other thing that we need to fix is we have a write register. We have a write register. How do I say this? We have a write register function, and this write register function is where, like I said, like I was just explaining, that mutex needs to be in place. You need to have the mutex so that you can write to that register. Otherwise, you can't write to that register, because writing to that register is how you control the device. And basically, what I would like to do is we have a few incantations of writing to registers across the file or across the driver. What I want to do is consolidate them all into one section, and then have that section be the one that uses the mutex, and then that way we have a secure, safe code, as we say. Inside we have a SPI configure function, and in this SPI configure function, we basically want to we basically want to configure the device. Just one. Yeah, sorry about that. Just needed to get rid of some background noise. So, okay, cool. So inside this configure function is where I've realized we have some overstepping. And basically what is happening here is we need to do this operation. There's this operation here. We need to build this 8-bit byte, the one that contains the clock rate, the mode, and the order. Well, LSB or MSB, and the CPOL and C phase rates, and then also we need to check which clock rate it is that the user is trying to use, and then we can set that. So inside that also needs some change. Basically, right now we're just basically writing the mode into the mode, which is an 8-bit, but it only contains the CPOL and C phase mode. And then now this we added a transceive function. This is just an SPI implementation that is to be used. So SPI drivers, or drivers of SPI, drivers of peripherals that use SPI for communications will expect this function. So if you're implementing an SPI controller, what you need to do is implement an SPI transceive function that can be used. Now, for the most part, this transceive function works just fine for us. However, there's this there's these two sections. We write into a register here, and then a few, I think, in also in the receiving, we also write into a register and read from a register. What we want to do is to pull these writes and reads out so that we can call a function, and that function basically acquires the mutex before it does this. And this is where you need the mutex. So because remember, we control this SPI bridge by using I2C commands. So whenever we want to write or read from it, we need to make sure that no one else is writing or reading from it. That way we don't interrupt with what they're doing, interrupt what they're doing. Okay, cool. And then we have an SPI release. This is just basically uh, housekeeping so that the system does not have too many resources. And basically, what you want to do is release the controller once you're done with it. And then we have an initialize that is working mostly fine, but this initialize does the configure the wrong way. It writes a config. It writes it the wrong way, and we need to correct that. And then at the bottom of this all, we have a macro to define our driver and to find every time it's called out, and then to apply to find the source code for this and apply that source code for into that macro. And then we have a basic header that defines what functions we need to define. And then after that, we basically have, what is it? Yeah, remember this is a multifunctional device. So you need to implement an MFD multifunctional device. So in Zephyr, let me pull that up. So let me pull that up so you can see. Let's pull that up. Zephyr MFD. So yeah, multifunction device driver. So we're implementing a multifunction device driver, and basically we need to implement a multifunction profile for this driver that we're building so that we can use it. Okay, cool. And that's basically what it is. That's it. And we do have a binding for our actual SPI driver that allows you to put in the clock and the mode. And other than that, we define what bus it's on, and the bus is the multifunction device that we made just now. So bus NXP, and then if you see down here, we also have on bus NXP SC18IS606. Okay, cool. And yeah, that's mostly that. This is just a test. This also needs to change because this needs to follow. That's the old implementation. Needs to follow this implementation, which will change just in a moment. And then yeah, this is fine. This is okay. This is okay. This is just Zephyr has Zephyr has tests that are already built. So in order to leverage those tests, you just need to provide your driver code to those tests, and they will run your test. Uh, Basically, that is what we're doing here by providing overlays for the test that contain our driver. Amazing. Um, Let me check YouTube for any questions or any data before we jump into actually into how do you say pop chat out. Okay, cool. Chat has been popped out. We shall see if something happens. Uh, and then oh, where's the thing on? Okay, cool. So let's now jump into the code as I've explained. So let's go into our, let's first deal with our configuration so that our configuration can work right. Okay. Um, so that is SC18IS606. Yep. And what we need to do here is deal with configure. Yeah, I would say we still need to do it, and it doesn't have to hard to do it. So in here, let's um, build build build. Let's build SC18IS606 configuration byte. Okay, so wanna build this byte. Okay, that contains the clock rate, the mode, the order. And I think so. Let's say you int it underscore t. We usually use ret in Zephyr, and then let's make that 0. And then let's say result. Let's set the let's set let's start by setting let's see the order. Right? Is it order? Yeah, let's set MSB or LSB. Okay. So I think we can do CFG. So CFG is our config. We can just call it config. And then in config, let's pick operation. And then in here, and then we go SPI transfer. And then let's and it with that, and then let's shift it 4. Okay. So let's shift it 4 bits into let's shift it 5 bits into our register, into our byte. Okay, remember here. Oh, sorry, here we need to shift it here. And the reason we left shift well, right shifted it by 4 is so that we can adjust it on, as you see here, 4 bits, so that we can check whether it's MSB or LSB. And of course, I started this wrong. That's fine. Let's then now we have that byte. Now we have that byte, and then the next thing we need to do is deal with the mode. Int 8 underscore t mode. Let's say mode. So we do have wide size get, transfer control, hold on, lock on. We have a macro, I expect. No, we do have a macro that helps us select the mode get. So I think we have something like mode get. That helps. Yeah, get SPI clock paralysis. You see here. So let's use that and just build the mode. Okay. So we have so let's just get the mode. Okay. So SPI mode get, and then here we do config operation, and then here, and then let's one, so that we find it, and then I've forgotten how to. Can I do and? Can I do and? Like, sorry. Let me see. Yes, let me Google and. Can I use um? Ah, yeah. I just can do that. Okay. So I'm just checking what set versus 3 so that basically it doesn't, you know, when you, both of them need to be true so that they're set. And then do that into that, and then you can do that, and you can say mode. I think we move that into 2 bits. And then let's do that. So now we have the mode, and then let's get frequency. Rec, and then if config. Can I switch on this? That would make it longer because then I would have to if and then no, okay, cool. Yeah, I would have to make some switch parameters, then I would be able to do that. So let's just let's do frequency, and then above or equal 180, 1, 2, 3. So in here, let's frec bit frec equals to 0, 0, 0, and then else config frequency. So I'm just following this guide here. Guide frequency greater than or equal to 400. Yeah. OB01. Yeah. Big frequency greater than or equal to 10. 100K? Yeah. Correct. Equals OB 0 else. Rec equals to 0B 1. Okay, cool. So now we have all the things, and then we have to say ret. Let's set ret equals correctly. Okay, let's see. Yeah. Yeah. So here we set the LSB MSB order, and then here we set the mode, and then here we set the frequency. And then now what we're free to do is number one is uh, I want to see the diff. I want to see the diff before I change this. What was I doing before? Was there some intermediate steps before? No, I have that byte. I can write that byte. It's fine. I want to see where I was getting the config to put into the config to put into oh, I'm setting the config backwards. Okay, cool. And then here I'm writing into our register. So cool. So here, instead of writing data.spi mode here, what I want to do is to write ret, and that basically changes it for us. Write reg ret, and also in initialize here. Rather than do this, I want to rather call this. I already have this code, so I'm not going to bother writing it again. Okay. Why? I'm sorry, I'm navigating line by line, but let's see. Okay, cool. So now we have info data. Okay, cool. I need to do just one moment. I think this is PFG. Data is data, but where am I getting SPI config from? I can still pass this here, PFG. Hmm. So I'm going to go. I want to see how you do your define. I want to see how you do your configure. Okay, so I think we want to build it. I think we want to build it. C18IS606. I think we want to build it. Can I say, can I build a, can I build a config here? Can I build a config here so that I can use that? Draft SCI config my config. Uh, I want dot. Dot frequency. What are we getting? Sorry, dot frequency dot SPI config. So now I have to open SPI config. Frequency operation equals data dot. This is gonna be a problem. It's gonna be a problem because I'll put the mode in it. I'm not so sure this will work, but I don't really care whether it works. The reason being, my config. It doesn't need to work because it doesn't. This doesn't need to work. The initial one does not need to work. The reason being is it needs to just let's see, give configuration fail. um, um, screen. Okay, cool. So now let's go back here. Screen. To the example driver display west build dash dash v for disco dash v activate. Yeah. Let's build that. Let's see if that can. Let's see if that works. Let's build and flash it. If that works, then we're good. And meanwhile, I can take some questions. I can take some questions in the meanwhile. See. So far. West flash. Open OCD. Yep. Driver works. Let's look at the. Yeah. Driver works. So cool. I think we should commit that. Git status. Git add drivers. Clear. Git status. Git add drivers. Okay. Clear. This page. Look at what we just did. We removed that comment. We made a configuration byte, and we configured it. And then at the end, we stopped writing to register, and we just called configure, and that works for us. Okay. Git commit /m drivers SCI SC18IS606 do proper configuration of the bridge. Okay, so that's the first one. That's the first one that's been done. Okay, cool. So the first change, that the first bit that we needed to work has worked. The next thing that we need to do now is to move the. Okay, cool. Let's just look at the code. It's easier. So initialize this has been fixed. So now we need to move this one, this two. So there's two operations here. Okay, first of all, let's find incantations of write reg. Basically, by the end of this function should disappear. So it's only in two places. There's only one more place it's used. Yeah, this is going to be removed just now. Amazing. Okay, cool. So now let's go and look at what we need to change. So configure, we fixed. It's transceive that we need to fix. Now, whenever transceive is happening, we need to either the first thing we need to do. C18. I'll show you what I want us to do. Good thing it exists in the Zephyr code base already, so we can look at it. So if we go here, this is a driver of the same. This is a UART to I2C bridge. What we want to do is whenever we're doing a transfer message, as you can see here, whenever we're doing a transfer message, oh, this is just a normal transfer, not an I2C transfer. Basically, whenever we're doing a UART transfer, where's UART? Whenever we're sending data out, please show it to me. Yeah, no, leave the verify out. Transfer is fine. Yeah, SCIM transfer. So this one. So you see, whenever we're doing a transfer, the first thing that happens is a mutex locks the device, and then once we are done with the device, we release the device. And we want to implement the transfer so that we avoid calling write reg and read reg inside the code. We don't want the code to always do writes and reads from one place. Okay, cool. So let's see, what does this take? So this takes the device, takes some data, takes length, takes some data, takes length. That's really it. In fact, I'm going to copy this. Okay, cool. So I'm going to copy that. Actually, let's put it in, let's see, 18IS606. Let's put it in the header. So let's look at this. So we accept a device, we accept the transfer data, we accept the device, we accept the transfer data, we accept the RX data. Okay. So let's do a brief for this. First of all, let's rename it the way we want it to be. So let's do NXP SC18IS606 1020. Okay, I might have. I could stop. I'm going to stop this stream on the top of the hour, and I'll stop the stream on top of the hour. But I will keep on implementing this and have it out so that you guys can see. If you do want me to continue the stream and you're here, just leave a comment, and I can always continue the stream. So, release the no transfer data using I2C to or from the bridge this routine implements the synchronization between the SPI controller and gpio controller. Let's see. together. So let's do add param dev. Dev is dev SC18IS606 bridge. Add param tx data. Data to be sent out. At param tx len tx data length at param rx data container to receive data at param rx len size of expected receipt at ret val 0 transfer success at ret val epalm I think SC187. Let's look at that head. Fine. Fine. Let's see. E again. Okay, cool. I see. You know, okay. E again. So device did not complete and needs another task. And that's it. So basically that is what we want. And then I can just do this, or I don't know. Mm, mm, mm. Do I need, this is a header. Do I need, yeah, let's see, 187H. Okay. So first of all, we want to do include to be int h. That's fine. And then we want to do an if def it's a hash if def def Zephyr Yeah, just go to that. I can add all this one. Uh, uh, 2025, and then this is going to be tiny, tiny vision AI, okay, August, and then that is going to be I squared CSCI, yeah, 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 if you want it, IS, IS 6060, doesn't really matter. Okay, I think that, well, it's been an hour of streaming. I'm gonna work on the rest of this offline, and then we'll get back to this. Thank you all so much for coming today. That was an awesome sesh, and thank you all for the people who are sending in questions and suggestions, and that's amazing. We'll see where we go from there. Thank you so much. I'll tell you, we'll see about the links what we're streaming next week. Cheers. Wait, I didn't really explain what happened there. So before we just jump off, so we've added we have added, should I just persist and push this through? So we have added this um, API in our driver, SC18IS606. Let's go in here. And then what we want to do in our, what we would like to do in our, what we would want to do in our, rather than this function, rather than the write register function, we want to have this function, this function. And this function's job will now be to actually handle the both transfers, okay? And in here, we're going to now the implement the read and the write from the device. Um, yeah, that's really it. I'm gonna do this offline. I'm gonna push the code, and then it'll be up there and out there for sure. I've said that a few times. Perhaps I should do it here, but mm, let's see. Mm, yeah, cool. I think the better decision is to do it offline. Thank you all for coming today. Thank you all for attending, and thank you for the questions, um, for the likes, and for the comments. Remember, if you want to help me do this, uh, send some comments below and help me know what I can do next time. There you go. Um, let's go here. End the stream.